This is quantum chemistry and machine learning for primary school students. Tejas did silicon monoxide this week, did some calculations, got a potential energy curve for the silicon atom binding to the oxygen atom. We got 3 different potential energy curves with 3 different methods. Gareth did sililidene. This is silicon bound to hydrogen. Again, we have a bunch of potential energy curves, slightly different well depth, slightly different equilibrium bond distance, but similar shape. Harvey did nitrogen hydride. We had Abdul do the diatomic carbon monofluoride, again with the same 3 methods. Sukrit did phosphorus monohydride. Everyone did a really excellent job on this task. Dulain did arsenic monohydride. Mrinal did calcium monohydride. Mia did phosphorus monofluoride. Mehmet did bromine monoxide. Aimun did 2 molecules. Aimun did chlorine dimer and carbon monochloride. And Hemant actually did carbon monosulfide plus also the cation. So you remove an electron and the potential energy curve has not too different of a shape, but the energy is much higher. Okay, and this is an example of a potential energy curve that I have calculated. This is something that I did in the past. This is something that has been published in a scientific journal. It's more publication quality, and there's a couple things different about this diagram compared to the other diagrams here. Okay, so is anyone able to observe? You can unmute yourself. Let me know what you noticed that's different about my diagram compared to everyone else's.
You have the straight line, the V equals those labels.
Yes, okay, so there's these horizontal lines here. So apart from the fact that I used LaTeX to make my axes labels look very nice and the molecular formula look very nice with the proper subscript, apart from the fact that I used LaTeX, which you all know how to use, I also have these vibrational quantum numbers. And what that means is, so you all understand a potential energy curve, it's common sense, right? We take 2 different atoms, and as they have different distances between them, there's going to be a different energy. And so that's how we get this potential energy curve. But those 2 atoms, they can vibrate with respect to each other. The molecule can vibrate. And the molecule can vibrate fast, or it can vibrate more slowly. If it's vibrating very fast, that means it's vibrating with a lot of energy, or a lot of vibrational energy. And if it's vibrating more slowly, then that means it's vibrating with less vibrational energy. And in quantum mechanics, this is the whole thing about quantum mechanics, you can't just vibrate with any energy level you want, with any amount of energy you want. In quantum mechanics, energies are restricted, they're quantized. That means that there's discrete levels that are allowed, and the molecule doesn't vibrate with energies in between these discrete energy levels that are allowed. So these are all vibrational quantum numbers. These are basically levels that are allowed for vibrations. And the molecule can be vibrating with V equals 4, that much energy in the vibration, or it could be vibrating with V equals 1, this much energy in the vibration. And it can also fall from V equals 4 to V equals 1, meaning that it falls from vibrating with a lot of energy to having a small amount of vibrational energy. And when it does that, it releases some energy. And the amount of energy that it releases is going to be the difference between these 2 energy levels. Okay? And so you can tell, now I showed you several different potential energy curves for several different molecules. They all look different. For every molecule, there is a specific potential energy curve. And so because there's a different potential energy curve for each molecule, it also, I haven't explained it in great detail, but these levels, they are dependent on the shape of the curve, and therefore these spacings between these levels will also depend on the molecule. So if you have lithium 2 versus if you have hydrogen 2, you'll have different spacings, and therefore the energy differences corresponding to the amount of energy released when you fall from a high vibrational level to a low vibrational level, those are going to be different. And so in some sense, these vibrational energy differences characterize the molecule. So if we're looking at the spectrum, which is basically a bunch of records of energies released by this molecule, if we're looking at the spectrum, we can decide whether this is the spectrum of water molecule or a lithium-2 molecule or sodium chloride or whatever. And that's how we're able to know that there's carbon dioxide in the atmosphere of Venus without even going there. This is how we know that there's water on Mars. This is how we might be able to find life on other planets, by finding maybe organic molecules on other planets, maybe finding water on other planets. So this is spectroscopy. It's a very, very highly applicable area of science, one of the most applicable areas of science, one of the most practical and useful areas of science, one of the most precise areas of science as well. There's spectroscopy that's used for detecting counterfeit currency. There's spectroscopy that's used for finding pollutants in the atmosphere, for detecting carbon monoxide levels, carbon dioxide levels, for detecting impurities in gasoline. So spectroscopy is extremely useful, and it all goes down to quantum mechanics, this one principle that I've just explained right here. So now everyone's probably wondering, you've done all these calculations, you've calculated all these potential energy curves. Everyone is probably wondering, what are these frozen values? You told me to use frozen equals 5 or frozen equals 9. You just told me to use that. I didn't understand what's going on. Now I'm going to explain that, okay? So calculating energies gets harder and harder as we increase the number of electrons in the system. See Quantum Chemistry for High School Students if you want to get more information about why that is. I explained Slater determinants, and I explained how when you have more electrons, they have to be, the wave functions have to be antisymmetric with respect to exchanging two electrons. I explained all that stuff and the concept of Slater determinants and all that. And so if you want to understand how expensive does the calculation get as we increase the number of electrons and how big of a problem this really is, you can watch that video on YouTube, Quantum Chemistry for High School Students, on my YouTube channel. But the fact that calculating energies gets harder and harder, in fact, pretty much impossible as you get too many electrons, that's not such a big problem, because most of the action happens between electrons outside of noble gas cores. I'm going to explain what that means in a second. But basically, if an atom is binding to another atom and forming a molecule, most of the action is happening. Not all of the electrons are playing the same amount of role in that interaction. So we're going to use something called the frozen core approximation. To understand what this is, you have to understand the concept of noble gas cores. And since this is primary school, we might not know what noble gas is. Gases are just the elements on the rightmost side of the periodic table. So these helium, neon, argon, these are the noble gases. And a noble gas core is basically all of the electrons that are in that noble gas. So neon, it has 10 electrons. You can count them by looking at the number in the top left corner here. So neon has 10 electrons. So if I have the atom sulfur, the first 10 electrons, we just call that the neon core. Okay, we're just going to call that the neon core. And we're going to freeze all of the neon core electrons. So we're going to draw a line, and whatever the largest noble gas before the atom is, in this case it's neon, we're going to freeze these electrons. We're going to make the approximation that all of the bonding is going to happen, most of the bonding, not all of the bonding, but most of the interaction energy is going to come from the aluminum, silicon, phosphorus, and sulfur electrons, and the sodium and magnesium electrons. So just that's maybe not the best way to explain it, but we have a bunch of electrons associated with these atoms in some sense, and we're going to consider those electrons when doing these calculations. And then all of these electrons are going to be frozen. It's going to make the calculation slightly less accurate, but a lot less expensive. So in this case, neon is number 10. There's 10 electrons in neon. We're going to freeze them all. But in PySCF, we can't freeze individual electrons. We're going to freeze electron pairs. So we're never going to freeze just one electron. Can everyone still hear me and see me? Sorry, my screen just blinked a little bit. Sorry about that. You know where to say something if you can't see me or hear me. So Because pi SCF only freezes electron pairs, we're going to take that number and divide it by 2. So 10 over 2 is 5. That's why frozen equals 5 for the sulfur atom, and also for the phosphorus atom and silicon atom and all of these atoms. Okay, so that's how we choose the frozen value. So now you try. Someone please unmute yourself and tell me the frozen value for arsenic. Mrinal. I see Mrinal is unmuted. Can you, I can't hear you though. Unmuting yourself doesn't do anything if you don't have a microphone, so anyone else want to try? Maybe others can hear Mrinal. Can someone hear Mrinal? I can't hear Mrinal.
Is it audible?
Is it audible? I can hear you. Yes, you're audible. Yes. Abdul, do you want to guess the value for frozen? Did I go too fast?
Is it 9?
Very good. Yes. Argon has 18 electrons in it. Argon is the noble gas that's the largest noble gas that's smaller than arsenic. Argon has 18 electrons, but we're only freezing electron pairs, not electrons individually. So we're going to freeze 9 orbitals, so frozen equals 9. Thank you, Sukrit. That was a very good answer. How about helium? Someone else want to try helium? What should be the frozen value for helium? If you freeze 1 electron pair, how many electrons are you freezing?
All of them.
Basically 2 electrons. Then you're freezing every single electron. So this wasn't a trick question. This was actually exactly what I explained. Take the largest noble gas that's smaller than your atom and freeze all of those electrons. But there's a reason why I chose helium, because I want to make sure you really understand what's going on. So here there's no noble, if you draw that line, the line is above the entire periodic table. There's no electrons, there's no noble gases smaller than helium, so we're not going to freeze any electrons. If we were to freeze the smallest amount of electrons that we can freeze is 2, and if we freeze 2 electrons, then we're freezing the whole, all of the electrons, which is going to give us results that are maybe not as interesting as we want. And now for molecules, just add the frozen values for each atom. This is just one example of a frozen core approximation. Remember, I said over here, I didn't say the frozen core approximation. A lot of people call it the frozen core approximation, and that's what I typed at the beginning, but I actually changed the to because there's many ways you can choose which cores to freeze. I mean, you can also freeze not just up to the neon atom. You can also freeze up to the magnesium electrons as well, if you wanted to. So I'm just teaching you one method to choose the frozen core, and this is quite conventional. There's a lot of programs that do this by default. So for molecules, again, there's many conventions, but the default convention in a lot of software is to just add the frozen values for each atom. So for arsenic, we have 9. For magnesium, we have 5. So if we were to make a molecule where we have arsenic and magnesium bound together, we would have 14. So now you try it. We have cadmium and xenon. What should be the frozen value for this molecule? Someone else this time. We've had Sukrit, we've had Harvey, we've had Gareth. Anyone else? Mrinal is typing. Okay.
36.
Abdul, what did you say? 36?
36.
Yes, 36 is correct. Okay. We have 36 for 36 electrons frozen for cadmium, 36 electrons frozen for xenon. So that's actually 72 electrons, but since we're just counting the pairs, we have 36. So now another question for you. Cadmium xenon. Does this molecule exist? I'm just curious what you say about this. Does cadmium xenon exist? Gareth?
Maybe, but it's going to be pretty hard to make it.
Okay, that's an excellent answer. I was expecting people to say, no, no, no. In kindergarten, we learned that noble gases don't make molecules. But that was a very good answer. Maybe is actually the right answer. We are theoretical chemists now. We can calculate and predict potential energy curves for molecules that are hard to make in the lab. So just because in kindergarten they said that the xenon dimer doesn't exist or xenon doesn't bind to other atoms, that doesn't mean that you can't do a pi-SCF calculation and still get the interaction energy between those two atoms. And you can actually find that many of these noble gases actually do bond to other atoms. The helium dimer has a bound vibrational level. The neon dimer, argon dimer, all of these molecules actually exist. They're bound not using the theory that you would learn in school in the earliest stages, but they're bound more physically due to longer range interactions and things like that. Still, the electrons from one atom are going to be attracted to the protons in the other atom, whether it's two argon atoms or whether it's two neon atoms or whatever. So, like van der Waals interactions still exist. So you have physical forces rather than chemical interactions. But basically, cadmium, xenon, any two atoms, we can, as theoretical chemists now, we can calculate the potential energy curve for any two atoms. It doesn't matter whether or not it's been created in the lab so far or not. So that's a very good answer. Maybe it exists. You can do the calculation and see if there is actually a deep enough potential energy minimum to support vibrational levels. Now spin, same thing with frozen. I gave you spin values. I said use spin equals 3, use spin equals 2, but I didn't explain to you why you were asked to use those values when you did your calculations. Technically, the spin is the number of unpaired electrons divided by 2, because the spin of an electron, you'll learn in high school, the spin of an electron is half. So if you take the number of unpaired electrons and you divide them by 2, that's just how you calculate the total spin. In pi-SCF, we simply just don't divide by 2. So we take the number of unpaired electrons and that's it. So if we have just one unpaired electron, instead of the spin being 1/2, we're just going to say it's 1. Okay, that's just the way pi-SCF works. That's also the way MolPro works. And that's also the way a lot of programs work. This way we're using integers rather than floats. So we don't have floating point errors. We don't run into machine precision issues. And it's also just more convenient for programming to use integers. It's more convenient for the input file. MolPro uses this. pi-SCF uses this. Some programs have you input the spin multiplicity instead of the spin or the number of unpaired electrons. That's maybe a better way of doing it because the spin multiplicity is always an integer and you can actually type that integer into the program and it's actually the spin multiplicity. Here you're typing in the number of unpaired electrons and pretending that it's the spin, so that's a bit unideal. But a lot of programs actually just allow you to enter in the spin multiplicity instead. I'll talk more about spin multiplicity a couple slides from now. But for now, I just want to say, how do you choose the spin value for atoms? Remember, it's the number of unpaired electrons in pi-SCF. And you can just search this on Google. In high school, you're going to learn all of this. But for now, you can just search it on Google. How many unpaired electrons do we have here for H? How many unpaired electrons?
1.
1. And for helium? Harvey is unmuted. Gareth is unmuted. None, you said? 0, that's good. How about for nitrogen? How many unpaired electrons? 3. Very good, Abdul. Yes, very good. So basically, you know how to get the number of unpaired electrons. You know how to get the spin. For molecules, the answer is that we simply don't know. We don't know what spin value to use. It's not like this in high school, you're going to learn the theory behind this and you'll actually learn an algorithm for generating this diagram, this orbital box diagram for whatever atom you want. But for molecules, it's just impossible to do it in general. at least I'll tell you, there's no established algorithm that always works. And I'm going to explain that in a couple seconds. So what do we do? Option one, you can do energy calculations like you just did last week. You did energy calculations. So you can do those energy calculations with various different spin values, and you can see which one allows you to find the lowest energy. So you can scan all the different internuclear distances with spin equals 1, with spin equals 0, with spin equals 2, get your potential energy curves for all internuclear distances, for all different spins, and find which one has the lowest minimum. Or you could do something called geometry optimization with each spin, and that will also be a way to find which spin configuration gives you the lowest energy. So that will tell you what the ground state or stablest molecule energy spin is. Option two is you can do experiments in a lab. So you can do experiments in a lab and find out which spin configuration is the most stable. You can also do a hybrid approach. And then there's other options. I'm not going to list every single possible thing. I mean, there's molecular orbital theory, so you can try to use some theory, but that theory isn't always going to work. So there's a lot of different ways you can choose the spin value for a molecule. But these are less common. The first three options are the most important one. Gareth and Salma are saying that they can't hear me. Who is not able to hear me? Oh, Gareth is able to hear me. Great. Okay. So it's just that you can't hear other students. So that's okay, because whenever people are asking me questions or answering a question, I'm repeating what they're saying. So that should be okay. If anyone can't hear me, just say something in the chat. Okay. So how do we do this? Option two, for example, or option three, the hybrid approach. Either of these approaches, we might look at the literature. And if we look at the literature, oh, sorry, do you hear an echo? Selma, Gareth, can you hear an echo? Is that the problem? Now I have 3 people typing. No, everything is normal for me. Okay, Gareth is good. Sukrit is typing. Let's see what Sukrit says. Aimun is typing. Okay, for me it's normal too. Okay, Sukrit, last person to type. Let's see. Okay, so Sukrit is suggesting that Salma, the only person not able to hear me, it might be something on their end, because 3 people said that there's no problems, and no one else is writing comments either. So Salma, there's going to be a YouTube video at the end. You can watch that at the end. So we look at the literature, okay? So we look at these tables where they've done experiments or theoretical calculations and consolidated the two. They did an experiment and it's confirmed by molecular orbital theory or whatever other theory, Hartree-Fock theory or whatever it is. And basically there's an established ground state spin configuration for each molecule. So here we have pH, and what we have here is a notation for the electronic state of the molecule. This sigma, that is the molecular orbital angular momentum. So just like for atoms, you have S, P, D, F, G. You've all heard of that. So S, P, D, F, G, that means the angular momentum is 0, 1, 2, 3, 4. Angular momentum is often denoted by L, the letter L, the English letter L. For molecules, we don't use the letters S, P, D, F, G. Instead, we have sigma, pi, delta, phi. These are the Greek equivalent. The Greek equivalent of S is sigma. The Greek equivalent of P is pi. So we have sigma, pi, delta, phi, gamma. So, and likewise, the angular momentum, instead of using the letter L, we're going to use the Greek letter lambda. So that's what this is. That's just the electronic state angular momentum, whether it's 0, 1, 2, 3, 4, whether it's sigma, pi, delta, phi. And in the top left corner, we have 2s plus 1. This is the spin multiplicity that I was mentioning 2 slides ago. 2s plus 1 is the spin multiplicity, where s is the spin. So in this case, we have a spin multiplicity of 3. What is the s value? This slide has been up for so long now, you must have been able to determine what s equals. So let's see someone unmute themselves.
V1.
Yes, 1 times 2 plus 1, that's 3. Now what about in pi SCF? What value are we going to use in pi SCF? The real spin is equal to 1, but in pi SCF, what are we going to enter?
2.
Very good. I was worried someone was going to divide by 2 and get half, but the real answer is 2, because in pi SCF, we don't divide by 2, which means that to go from the real spin to the pi SCF spin, we just multiply by 2. So the correct answer is 2. Very good answer. So people have asked on Matter Modeling Stack Exchange, what is the total spin and or multiplicity for transition metal ions? And they're talking about molecular ions. That title should be edited. And I gave an answer in 2020. I gave an answer with a lot of explanation about everything. But I gave this example, iron dimer, iron bonded to iron, Fe2. And I gave this table. And this table is basically there to show you that you basically can't determine the spin, at least in 2023. We don't have good enough theory yet to do it in all cases. So in 1975, there's this experiment where they were not able to come up with a conclusion. The multiple states are probably very close to each other at the bottom of that potential energy well. And years later, there's a computational study, and they did what I told you. They chose various different spin. Well, I haven't looked at the paper, but I'm assuming that what they did is they chose a bunch of different spin configurations and did calculations, potential energy curves, just like you did. And they found that the one with the lowest ground state energy, the lowest equilibrium energy, was this one with a spin multiplicity of 7. And a molecular orbital angular momentum value of what? Does someone want to try to answer that? We haven't heard yet from Tejas or Sam. Hemant is typing L equals 3. I don't think that is correct. Anyone else want to try? Was I going too fast when I talked about orbital angular momentum? Okay, L equals 2. And you guys are typing L, but I would like you to type lambda, capital lambda, because this is a molecule, not an atom. So that's why we have sigma pi delta instead of SPDF. Okay, the reason it's lambda equals 2 is because lambda equals 0 is for the sigma states, lambda equals 1 is for the pi states, lambda equals 2 is for the delta states. Excellent. So they found that it was a spin multiplicity of 7 and angular momentum of the ground state was the quantum number 2. And then the next year there was an experimental study. They say we agree that the spin multiplicity is 7, but we disagree with the orbital angular momentum that you determined. So your calculations were wrong. And then the next year there's another experiment. They say actually we agree that it's a delta state. We agree that the molecular orbital angular momentum is 2. And we also agree with your spin multiplicities too. But we're not sure whether it's ungerade or gerade. And then there's more and more studies over the years. And in 2002, now we have bigger computers and more sophisticated calculations, and they determined they're able to find something that the experiments were not able to find. That the ground state actually has a multiplicity of 9. And then there's these combined hybrid approaches. In 2003, you have someone publishing a paper saying that the ground state is 7 delta U. That's originally what people were saying in 1982. But then in 2014, people are saying now with more sophisticated calculations with supercomputers that by then would have had at least 128 gigabytes of RAM. Not that they would have been using all of that RAM, but the calculations are getting much more sophisticated now, and they're saying now it's this spin of 7, the spin multiplicity of 7 is not correct. And then in 2015, now this is so recent, they even had the internet by now. They're able to do calculations, much more thorough calculations, and they decide we really don't know what the molecular ground state is. We don't know the spin multiplicity. And that's why I say that you can't know. It's not like there's a theory that just automatically gives you the correct answer every time, as there is for atoms, or as we believe it to be true for atoms, because there's an algorithm that you're going to learn in high school, and that algorithm, if you use that algorithm, you're going to get results that match experiments. For molecules, maybe for H2 and for lithium 2 and some very basic molecules, you might be able to use molecular orbital theory and get accurate results. But in general, we can't do it without doing experiments and computations and consolidating the two. So we have been using, what have you been doing all this time? You've been using a hybrid approach. I was doing this behind the scenes. You were just doing calculations. I would give you a spin value. You didn't know that I was doing this, but I was looking at the literature. I was finding the best spin value from the literature, which is a combination of experimental and computational results. Often there's an experiment. The experiment suggests that the ground state is a singlet state, spin multiplicity of 1. And then that also matches what our theoretical understanding is and matches ab initio computational calculations. So basically it's established, like you can imagine there being a committee that establishes this is what we believe the ground state spin multiplicity is. Now, instead of a committee like IUPAC, it's just the scientific community comes to a consensus in a more loose way. Now, our hybrid approach is that we got this value from the literature, and then we did pure calculations using that spin value. So we got the spin value, and then we calculated the potential energy curve. Now, Mia did phosphorus monofluoride. This molecule's potential energy curve, can anyone say, does anyone notice anything unusual about this potential energy curve?
It seems to have 2 minimums.
Okay, you're saying there's a small minimum here. You could have also said that there's a barrier. You might have also said that there's a shelf. Now that is actually okay. I published a paper in 2015 on the lithium dimer, Li2, and the lithium dimer has this type of shelf, okay? It even has maybe a double minimum, or close to a double minimum, maybe a small shelf over here, okay? So, very sophisticated calculation, and this is a very highly excited state of the lithium dimer. It's not the ground state of the lithium dimer, but it's possible for molecules to have that shape. I'm not saying that this molecule that Mia was working on actually does have that shape, because these calculations, I'm not saying that they used the most accurate methods, but in this approximation, within this approximation that was made, the basis set that was used and everything, that's what we observed here. And that's okay, because even the most sophisticated calculations for some molecules will present themselves to show a barrier or a shelf or a double minimum. And so some of you might have heard of the term particle in a box, okay? Now, a particle in a box, when you're studying a particle in a box, which you might even look at in high school, as you widen the box, the supported energy levels come much closer together. And as you make the box narrower, the supported energy levels get further apart. And so that's why we see when the potential energy curve is a lot wider, you actually have energy levels that come very close together. And when the particle in the box, when the box is narrower, you get energy levels that are more wide. So the particle in the box is just an easy way to study this type of thing. We just pretend that the potential has straight lines, a horizontal minimum, and then another straight line. But in reality, you have very weird shapes where you can't solve it with a paper and pencil. You instead solve for these vibrational energy levels on a computer. Now, Mehmet did calculations on bromine monoxide, and I want someone to unmute themselves and tell me what they find in this potential energy curve to look slightly strange. And don't answer if you're one of the people who had this problem. If you're one of the people that has already experienced this problem, or we already talked about this, or you read about it somewhere, I don't want you to answer. Someone who did their calculation and the calculation came out perfectly the first time, can you tell me something you observe here which you find to be unusual?
There's an asymptote that's not zero.
Yes, there's an asymptote that is not zero. So there's also these fluctuations here, but everyone got that towards dissociation. It becomes very difficult to converge calculations as you get close to dissociation. And you're going to see the reason for that in a couple slides. In a couple slides, you're going to see exactly why that's happening, or exactly why I think it's happening. But the asymptotes should go to zero. So here, I asked for any comments here, and you gave me the comment. The CCSD and CCSD parenthesis T calculations seem to be going to the correct asymptote of zero. UHF seems to be going to a much higher asymptote. Total energies are less interesting than energy differences, okay? I can give you the total energy, the sum of all electronic energies and all the electrons in my entire body, and you can calculate my total electronic energy, okay? The fact that I have a lot of energy, that's a subjective, that's a subjective matter in some sense. What's more interesting is my energy relative to other people. Do I have more energy than Boris Johnson? Do I have more energy than Lionel Messi? Okay, you can say Lionel Messi has a lot more energy than I do. Okay, that actually means something. Someone has more energy than the other person. But if you just wake up in the morning and say, I have low energy today, well, what does that mean? Maybe you have more energy than everyone else on the planet, but you say you have low energy. So total energies are less interesting than energy differences. So molecular energies are reported relative to atomic energies. That way we're comparing it to something. And in terms of atomic energies, if the internuclear distance between two atoms is infinity, if it's very, very large, we basically have two individual atoms which are not interacting anymore. The forces are just too weak. The 1 over r squared in your forces is just basically zero when r is extremely large. Or if I have this arrow here, it's like r tends to infinity, then the interaction tends to zero, or the forces tend to zero. And so basically, if we have the atoms very far apart, we basically just have two individual atoms. The total energy is just the sum of the two individual energies, and with no molecular interaction energy going on. Okay? And so that means that the molecule, when r equals 1 billion angstroms, should basically have the same energy as two individual atoms that are not interacting at all. And so that's why when we're looking at molecular energies relative to atomic energies, the molecular energy relative to the sum of the atomic energies, well, the molecular energy should be the same as the sum of the atomic energies when r equals infinity. So basically, the relative energy should be zero. Now here is a diagram. Remember, I talked about SPDF. Atoms can exist with various different angular momenta. So you have S, P, D would be higher than this. You have here just two states for an atom, S and P, and you can have 8 different types of molecules. The angular momentum for the molecule can be sigma, it can be pi, you can have spin multiplicity of 3, spin multiplicity of 1, you can have ungerade, you can have gerade. So you have 8 different, you have 2 times 2 times 2, 8 different molecules just when there's 2 atoms. So you're going to get excited about atomic physics in high school when you learn about this SPDF, but then in university, you're going to get even more excited because there's such a rich diversity of molecules that you can have. The diversity of molecules is just amazing. In fact, for lithium-2, we just have 8 molecules dissociating to these two asymptotes. But for other molecules like the iron dimer, which I mentioned before, you have a delta state. Well, you have probably a d orbital. That's why you have delta molecular states. And when you have d, you have so many different possibilities. You can have s plus d, p plus d, d plus d. You can have so many different possibilities. And basically what happens is that there's so many potential energy curves. Remember, I showed you the spin multiplicity of 7 and 9. Those are basically so close together that neither the experiments nor the theory or calculations have been able to conclude which state is that molecule living in most comfortably. So this is just to show molecular diversity is just amazing. The number of, if you love quantum mechanics, you'll love quantum chemistry. Now, relativity and quantum electrodynamics. Most people have heard of relativity in the context of Albert Einstein. That's classical relativity, okay? So objects, big objects that are moving, Newton would say that F equals ma. Einstein says that there's a slight correction to that formula, especially when those objects are moving close to the speed of light. That is classical relativity. It's relativity applied to classical mechanics. Now let's talk about quantum mechanics for a second. The Schrödinger equation allows us to predict, well, the Schrödinger equation tells us that there's quantized energy levels like n equals 1 and n equals 2 for the hydrogen atom. The Schrödinger equation was written down, or it was published in 1926. He got the Nobel Prize for it in 1933. And this is basically a classical quantum equation. Classical meaning that it doesn't consider any particles moving close to the speed of the light. In reality, electrons are moving very fast. You might have heard that somewhere. Electrons move very fast. They're actually moving close to the speed of light compared to how fast you're running, I guess. So they're a lot more relativistic than humans are. And so a quantum relativity theory was published in 1928 by Paul Adrien Maurice Dirac. The equation, the Dirac equation, was actually arrived at by Erwin Schrödinger before he arrived at the Schrödinger equation. So maybe 1925 or something like that. Erwin Schrödinger actually arrived at the Dirac equation, but he abandoned it because he said, I can't solve this for more than one electron. This is useless. I'm going to try something else. And the Schrödinger equation, you can actually solve it for how many electrons have you done? Some of you have done molecules like arsenic hydride, which has lots of electrons, and you're solving literally the Schrödinger equation. But that's numerically, so I guess I'm being unfair. But at least in terms of atoms, well, okay, you can't do it analytically for more than one electron. But the problem with the Dirac equation is that it's not even manifestly covariant for more than one electron. So it's not even satisfying the principles of Einstein's classical relativity for more than one electron. So that's the problem with the Dirac equation. So Schrödinger abandoned it. Dirac published it 2 years later, and he shared the Nobel Prize with Erwin Schrödinger. And so this is relativity in a quantum context. So it's a bit beyond what Einstein talked about in 1905, which was relativity in a classical context. Now, science doesn't stop there. Science doesn't stop in 1933. There's quantum electrodynamics. This one example of quantum electrodynamics showing its true colors is this very small shift in energy you see here, the Lamb shift. Okay, it's a very small energy splitting. Lamb got the Nobel Prize for doing an experiment where Lamb determined that basically the hydrogen atom can exist in these two different states, not just these three states, but all four of these states. And it took a long time to come up with a theory that could actually explain that or predict it a priori without, you should be able, a good theory will be able to predict this without even seeing the experiment. Just as the Schrödinger equation tells you immediately that there's more than one eigenvalue and that the eigenvalues are spaced apart. Quantum electrodynamics has a long history. A lot of people got the Nobel Prize for this in 1965. Richard Feynman. You may have heard of Richard Feynman, very famous guy. He wrote "Surely You're Joking, Mr. Feynman," and if you've heard of the Challenger spaceship that failed out in outer space, and there's people that died because of it. Feynman was the one that discovered the reason why that happened. So really, really, really famous physicist. He shared that Nobel Prize with Julian Schwinger and Shinichiro Tominaga. And but it wasn't just the three of them that developed this quantum electrodynamics theory. Freeman Dyson, who just died in 2020 during one of the COVID lockdowns, and Hans Bethe, and a lot of... Paul Adrien Maurice Dirac was actually playing around with quantum electrodynamics in the 1920s. He quantized the electromagnetic field, and Enrico Fermi was working on quantum electrodynamics at the time. But they had this problem. There's like infinite sums that are not converging. You can just imagine that there's like some very big sums that are not converging, and there's a real problem with the mathematics here. And from around 1946 to 1948, Hans Bethe and a lot of other people started coming up with mathematical techniques to treat this problem. It's called renormalization. And you may have heard, like, because in primary school you don't learn about all this stuff, but you may have heard some popular science. You might have seen the movie The Man Who Knew Infinity. That was Ramanujan. Ramanujan is famous for these infinite sums like 1 plus 2 plus 3 plus 4 plus 5. In school, you learn that just diverges. It doesn't converge to anything. So in school, they teach you that just becomes, there's no answer. It just doesn't diverge. But Ramanujan came up with a way to, he didn't come up with this way, but Ramanujan would say that it's negative 1 over 12. 1 plus 2 plus 3 plus 4 up to, as many integers as you can find. And he would say it's minus 1 over 12. And that's a different way of looking at these infinite sums. And so this renormalization technique is basically a technique that allows us to treat some of these mathematical problems with infinite sums that Paul Adrien Maurice Dirac and Enrico Fermi were experiencing in the 1920s and 30s. So that was all sorted out in the 1940s, and 3 people got the Nobel Prize for it. So that's this tiny shift over here, a very small shift. It took a long time before experiments could see this shift. But it's a real shift that does exist. And so if you look in the molecular context, this is a paper that I published in 2015, okay? This is lithium dimer again, but a specific state of the lithium dimer, which happens to have this splitting over here. Now you have doublet S plus doublet P. Here you have doublet S and doublet P. So if you have an S state and a P state combining with each other, and they both have the same spin, S plus P versus a different S plus P. S plus P is just S plus P. Though if there's an energy for S and an energy for P, for lithium in the S state and lithium in the P state, then why is there a difference between these two? And the reason is because this is P3 halves and this is P1 half. So this is like, for the lithium atom, this is analogous to the Lamb shift that was observed in hydrogen over here. And you can see that there's 4 different molecular states here, 2 of them going towards this one and 2 of them. In reality, there's way more molecular states, but these are just the molecular states with triplet pi U symmetry. So with triplet pi U symmetry, you have a molecule with a potential energy curve, which actually splits into 4 different potential energy curves when you introduce quantum electrodynamics. Well, we don't actually have to introduce quantum electrodynamics, but that's basically the background about this type of splitting over here. Now look at the size of this. This splitting here is 0.335 inverse centimeters. You remember now, you did calculations over the last 2 weeks. You remember calculating potential energy curves where you had like the well depth was 80,000 80,000 inverse centimeters. 80,000 inverse centimeters. And this is 0.335 inverse centimeters. So accuracy is important. when you're wondering, like, why is it that I have to redo these calculations because the energy asymptote was not zero, you know, it's very important. If you can see on a figure with that type of scale that the energy asymptote is not zero, that's a huge difference, because these quantum electrodynamic effects, they come into play at the 0.335 inverse centimeter level here. Okay, and you can just see in terms of vibrational quantum numbers, 70 vibrational levels, and you're here at 8 inverse centimeters of energy. Here we're at 2 inverse centimeters of energy. Here we're at 0.5 inverse centimeters of energy. We cannot even see it on this diagram. So that's why this diagram is there, to show you these levels. Okay, now everyone in elementary school has done a line of best fit. You have some scatter plot data, and you draw a line with a ruler. You have some graphing paper, and you draw this line. You try to make it the best possible line through that data. And you get y equals mx plus constant. We want to do the same thing with these potential energy curves that you calculated. You calculated 10,000 energy values for 10,000 different 10,000 different internuclear distances. You calculated 10,000 different points of energy. We want to now make a curve that goes through all this. This is the other difference between my curve. Remember, I asked you what's the difference between my curve and yours. Not only mine is publication quality with LaTeX labels and everything, not only does it have these horizontal lines, but I have a smooth curve here. These are just dots. These dots are, you know, they're not as pretty as these smooth curves. Okay, so how did we do this? We did fitting, or curve fitting, or least squares fitting, whatever you want to call it. Curve of best fit. Here we have the blue data, all those points, and then we have an orange curve that goes through it. And just like in elementary school so far, you've been doing y equals mx plus c. You've been drawing a line through those dots. We're doing the same thing here. dE is the depth at equilibrium. RE is the internuclear distance at equilibrium. And VE is just a constant. That's your C. So you have y equals a bunch of stuff times x, or, you know, a function of x, exponential of x, whatever, plus c. What we're left with, because we know what the depth is at equilibrium, we know what the internuclear distance is at equilibrium, we can find the beta of our function. This is free for fitting, so we can fit that to the data. We can rearrange this formula, and we can just solve for beta of r, because we know everything on the left, or we can figure it out. Okay, we might be able to get it from experiments, or, you know, we can do very high precision calculations, figure out these. We can do geometry optimization, get RE, we can get DE. We can also fit these, but ultimately it's easy to get RE and DE. So the left side of this equation is known, and so for each internuclear distance r, V of r, this variable over here, determines the appropriate beta of r. So as long as you have that energy that you calculated in pi SCF, then you can get the corresponding beta value for that internuclear distance. And that means that it takes 10,000 numbers to specify beta of r in this case. You have 10,000 internuclear distances and 10,000 energies, and we can therefore have 10,000 beta values corresponding to those 10,000 V of r values that you calculated in pi SCF. So now you have this function, okay, with beta exactly determined from the data. But that function, have we really learned anything here, or have we just copied everything from the data? Okay, have we learned anything transferable, or are we just like a photocopier that has just copied pixel by pixel? 10,000 pixels, we've just copied every single pixel and made our own version of that pixel. That's what a photocopier does. Does a photocopier learn anything? Is a photocopier intelligent? Is it as intelligent as ChatGPT? Is it an artificial intelligence? I don't think so. A photocopier is literally just copying a bunch of things. If you ask it a new question, if you give it a new thing to print, it's not going to know what to print because it hasn't learned anything. It has just copied things mechanically. Okay? So let's do machine learning. Let's actually learn something. Machine learning uses models. What is ChatGPT? ChatGPT is an example of an LLM, large language model. It's not the only LLM. There's Hugging Face and there's other open source ones. If you don't want to give your phone number to use ChatGPT, you have to verify your phone number and all that. If you don't want to give your phone number to OpenAI, then you can use Hugging Face or some open source version of ChatGPT. These are all just large language models. They're models, okay? So we're going to model beta of R as a polynomial in this case, just this function over here. We have a small number of trained parameters, beta 0, beta 1, beta 2, beta n, these coefficients. A small number of trained parameters is enough to predict the rest of the curve. Okay? So ChatGPT, it didn't memorize all of human knowledge. It encoded training data, then predicts answers. When you ask it a new question, it will try to come up with a question, with an answer based on how it was trained. So let's not memorize 10,000 energies that we calculated in PySCF. Let's encode 10,000 of those energies that we calculated in PySCF into just a small number of parameters and see how they predict the other energies for the potential energy curve. In 2011, I published this paper in Journal of Molecular Spectroscopy with Bob Leroy, the famous Bob Leroy from the Leroy radius. We had just 10 beta parameters, and we were able to build this potential energy curve for this molecule over here. And there was experimental data only up to v equals 7. So we took that experimental data and we fitted an empirical curve that basically reproduces all of this experimental data. But then we have 3,000 inverse centimeters of blank space where we don't know anything. But we actually trained a model to reproduce this data over here. And 2 years later, we didn't even know at the time that this was happening, but we published this paper in 2011. It took from 2007 to 2011, 4 years to publish that paper. And during that time, or slightly later, there was a group at the University of British Columbia, an experimental group that wanted to do experiments on this molecule. And in 2013, those experiments became successful, and I was a co-author along with Mariusz Semchuk and Kirk Madison. This was published in Physical Review A. And these energy levels over here were actually found experimentally and successfully based on the predictions from the model that was trained only on that data set over here. The missing levels were found, and the errors in the predictions were less than 1.3 inverse centimeters. Okay, that's very good considering that there's a 3,000 inverse centimeter gap here. So we trained the data based on this 1989 experiment. We trained the model based on that experiment, on the data from that experiment. And that model happens to be able to extrapolate very well. So if you ask, what is V equals 20? Just like you ask ChatGPT, what is the spin multiplicity for the iron dimer? And it tries to give you something. Here, you can ask our potential energy curve GPT, PEC GPT. You can ask it, what is the energy of the V equals 20 vibrational level in this molecule? And it gives you a number that is quite close to what was actually found experimentally. And in fact, this experiment would not have been possible without these predictions. That's another thing I will say. So let's do it. We have on the left this formula, which we already showed that we can, well, I already said that we can rearrange this formula for the potential energy curve. This function for the potential energy curve can be rearranged so that we have this on the left and beta of R on the right. And beta of R can be represented by this model. And now in this model, we have beta 0, beta 1, beta 2, beta 3, beta n. So we have all these beta coefficients. We're just going to put that in a vector. A vector, you'll learn what that is in high school, but a vector is just an array of numbers, just a bunch of numbers grouped together. And likewise, we have here x to the 0, x to the 1, x to the 2, x to the n. That we're going to put in a vector. And if we transpose this vector and we multiply it by this vector, we get exactly what we have over here, okay? Just the sum of all these products. Now, this is not primary school level anymore, but I can just tell you, everyone in primary school understands. I'm just saying I have this function here, and I'm just representing it in a more compact way. The thing on the left is y of r. The thing on the right is just x transpose beta. That's just a way of writing what we already have here. Okay, nothing too complicated. Now, in terms of, in high school, you might learn how to solve matrix vector equations, but this isn't just a simple matrix vector equation. This is a function. I'm mixing functions with vectors. I have a function equals a vector function times a vector. It's a little bit, I'm mixing things up here. But this function y of r, we know there's 10,000 internuclear distances at which we calculated the potential energies. So we have y of r0, y of r1, y of r2, y of rnv, where nv is the number of v values that we have. So we have a vector here now. We turned that function into a vector. We have a vector that describes all of these different values of this expression here. And likewise, here we have x to the 0, x to the 1, x to the 2. That's what we have here, x to the 0, x to the 1, x to the 2. When you transpose it, you get x to the 0, x to the 1, x to the 2. But now for each of those columns, we're going to have a lot of rows representing each internuclear distance. So we have a vector for each of those columns. We end up with a matrix, and so this complicated equation over there, mixing functions and vectors, we end up with just a matrix vector equation, y equals x times b. Okay, so y equals x times b, we know how to solve that. B beta equals x backslash y. That's easy to do in MATLAB or Julia or Octave. Harder to do in Python, but still possible to do. Now I'm reminding you, beta is just beta 0, beta 1, beta 2, all the parameters that we want to optimize or to train. When we train these parameters, we end up with a function. This is the model. The model is this polynomial over here. Beta of r is just a function that goes into this expression over here. That's just a function for the potential energy curve. We know everything else, the dissociation energy or depth at equilibrium and internuclear distance at equilibrium and all that. So we can basically get 10 beta parameters, just 10 constants that were trained based on the data. And with those 10 parameters, we actually have a model that's able to predict energies outside of the training data. And that's essentially one type of machine learning. Okay, so I hope that was interesting. Let's now talk about some of the calculations that were done by some of the students here. Aymoun did the chlorine dimer and carbon monochloride. So that's interesting. Two different diatomic molecules here. So Aymoun is ready to move on to triatomics. Here we have dichlorocarbon. Now, the potential energy curve is going to depend on this internuclear distance, and the angle here. Okay? Now, how are you going to plot these potential energy curves? Imagine here you have the x-axis, that's what you call it in primary school, the x-axis for this potential energy curve. You have the x-axis, you have a y-axis, you have a z-axis. You have all three of your axes with which you're familiar. All three axes are being used for the independent variables. So then where does the energy V go? How are you going to plot it? All three of the axes are already being used for the independent variables. Okay, so we end up with a hypersurface. Okay, and I just Googled I just typed into Google Images, beautiful potential energy surface, and I found this diagram. This was one of the first ones that I found, which is by, I just love this image. Out of all the ones I found, I liked this one. It was the prettiest. And it happens to be by a co-author of mine by the name of Richard Dawes. I published a paper on the ozone molecule with him. And so basically here we have a triatomic molecule interacting with an argon dimer. So this is argon-argon. And you have this hypersurface, which is in this case just compacted into something that we can visualize, because we can't visualize hypersurfaces very easily. And that's the type of thing that we would be doing for this triatomic molecule. Now, you spent 2 days doing a diatomic potential energy curve, 10,000 points for the internuclear distances along one direction. Now, imagine if you had to do 10,000 times 10,000 times 10,000 energy calculations. 10,000 is what? 10 to the exponent 4. So you have 10 to the exponent 4 times 10 to the exponent 4. You have 10 to the exponent 8, which is 100 million. Then you have 10 to the exponent 4 10 to the exponent 4 times 10 to the exponent 8. That's 10 to the exponent 12. That's trillion. Okay? You want to do a trillion calculations? You spent 2 days doing these calculations. Do you want to spend several months doing the potential energy surface for this? For a triatomic or pentaatomic molecule? Probably not. And that's why this fitting is very important, so that you can calculate just a few points and come up with a good model that represents the rest of the potential energy surface. Okay, so that is what the goal is over here. And ideally, in this hypersurface, if you take a slice, the R1 equals 0 slice, you will get a curve that looks like this. And if you take the R2 equals 0 slice, you'll get a curve that looks like this. Okay, when, well, it won't look exactly like that, but ultimately you understand that the information here will probably be embedded in some sense in this multi-dimensional figure over here. Now, the multi-dimensional version of curve fitting for potential energy surfaces has some open problems, and therefore there are opportunities for publications. For diatomics, we have been doing potential energy fitting for a long time. For triatomics and more complicated molecules, the models aren't as sophisticated as they have been. These papers that I showed you, 2015, 2011, 2009, those papers, that's really novel research that was done by Bob Leroy and I over the last, 15 years or so, and actually a bit more than that. But those sophisticated models for diatomics, we don't quite have those for triatomics yet. I know how to solve these problems, these open problems. I know how to solve them. But we just don't have anyone, we don't have enough manpower to actually apply them to molecules in published papers. Okay, ultimately, the statistics and machine learning community, they know how to do multidimensional fitting. Chemists and physicists and quantum mechanics people and computer scientists, they all have different areas of expertise. And the people with expertise in spectroscopy, physics, quantum mechanics, chemistry, don't necessarily have all of the expertise of computer scientists working in machine learning. Now, I have expertise in all of the areas, and I know how to solve this problem, but there's a reason why basically it's taken until 2023. We still have some open problems that need to be solved here, and that's why with enough training, everyone here, you all understand how to make diatomic potential energy surfaces. You all understand how least squares fitting works. You've all done a line of best fit in your primary school class. So, the linear algebra and stuff, that you might not understand all of it, but it will come together over time and you'll understand how the fitting is happening. So basically, you have all the ingredients, and now I think with my training, we might actually be able to do something very valuable to the scientific community here. Now, what about the possibility of publishing your diatomic potentials? That's what everyone's waiting for, right? Everyone's saying, I just spent 2 days calculating these energies in PySCF. When am I going to get my paper? You published something in 2009. You published something in 2011. Here I published something in 2009. Accurate analytic potentials for the lithium-2 molecule from 2 to 90 angstroms. How many people were telling me, hey, do I really have to go to 10 angstroms? Do I really have to go to 10 angstroms? Yes, you do. Okay, the long range behavior is C6 over R to the 6. That R to the 6, if you multiply your potentials by R to the power 6, internuclear distance to the power 6, you're going to get a very big, you're going to see that the curves are no longer flat. Okay, so it's not like there's nothing going on in the long range region. In fact, the long range region is the most important for physicists working on scattering problems and things like that. Ultra cold physics. There's a lot of people studying that right now. Studying fundamental physics. They're trying to unify gravity with quantum mechanics by studying these very heavy molecules and things, and using photoassociation of ultra cold molecules and things like that. People are trying to make quantum computers out of diatomic molecules. So there's a lot of interesting things going on in the long range region. Okay, now this is a paper that was published in Journal of Chemical Physics, 128 citations on Google Scholar, meaning that 128 different papers cited this paper or referenced it in some way. So diatomic potentials can be very interesting. If you can publish a paper on a diatomic molecule, it can be very valuable and interesting to the scientific community. Okay, but a publication doesn't happen after 2 days of calculations, I'm sorry to say. That paper I told you in 2011, I published that paper with Bob Leroy. It took 4 years to publish that, 2007 to 2011. But it was very rewarding in the end. Now, in the end, you have this potential energy curve for this lithium-2 molecule, and it goes from 2 to 90 angstroms and whatever. Once you have that potential energy curve, you have an equilibrium bond length, which you can derive from the potential energy curve, 267.3 picometers. Have you ever wondered how you obtain that value? Okay. For various different electronic states of the lithium dimer, remember I told you about the sigma states and the pi states and the triplets and the singlets. For various different states, you have bond lengths and even dissociation energies and uncertainties in those values, which are derived from this type of potential energy curve analysis, potentiology, the study of potential energy curves. Okay, and you can see my name as a co-author is on 4 of these publications here, which are referenced when people they want to look up how big is the lithium-2 molecule. You can look it up. You can find the data. It comes from a potential energy curve, something that I calculated. So Aymoun, you did chlorine dimer. You can determine the bond length to a higher precision than any experiment that's ever been done before. Hopefully, maybe. I'm not promising anything, but hopefully that's what happens. Abdul, you worked on a molecule. Tejas, Sukrit, Sam, Salma. Sam didn't do diatomic molecules yet, but Mrinal, Mia, Hemanth, Harvey, Gareth, Dulaine, all of you have done this, right? So this is something possible. It's a contribution you can make to science. Now you used the basis set 321G, which is one of the simplest and smallest basis sets in existence. It's not a very accurate calculation when you're using the 321G basis set. And you use this method, coupled cluster with singles, doubles, and perturbative triples. If you want to know what that means, just look at the Quantum Chemistry for High School Students YouTube video. It explains all of that. Okay? So you use this method and this basis set. Now, in reality, the calculation with only including single and double excitations is different from if you include triple excitations perturbatively versus if you include triple excitations completely, or if you include quadruple excitations perturbatively. Look, the numbers are different. Okay, the numbers are changing all the way until you get to full configuration interaction. Okay, so now this 6, 7, 8th digit, the 8th decimal point in Hartree units isn't that important when you convert to inverse centimeters. We care about 0.3 inverse centimeter accuracy for that quantum electrodynamics thing I showed you. That is going to be basically like the micro Hartree digit is the micro Hartree, or maybe one more digit is enough for that. So this one with the septuples, probably this one is okay. Like I would say the CCS-DTQP parenthesis H, that's enough for what we were doing there, okay? But you would have to do these more expensive calculations. You can't just do these 2 days of calculations on a laptop, okay, and publish it. It's got to be a good enough accuracy to publish before it becomes worthwhile to write a paper about it. And so if you want to know what HF, Hartree-Fock, and CCSD and all of this stuff is, I explained all of that in Quantum Mechanics for High School Students. Hartree-Fock, CCSD, I explained that in extreme detail, even full configuration interaction. Now, in terms of basis sets, 321G is just like so small. I don't even do calculations in 321G anymore. I do calculations with these basis sets: double zeta, triple zeta, quadruple zeta, 5 zeta, 6 zeta, 7 zeta, 8 zeta, 9 zeta. These are bigger and bigger basis sets, and you can see that the energy also changes as you change the size of the basis set. Okay? And eventually, and you'll never get convergence this way, but what we do is something called extrapolations, complete CBS, complete basis set extrapolations. We basically, the extrapolations are converged, but the raw values are not converged. So we'll get convergence with respect to basis set size, convergence with respect to how the electron correlation is treated, and we get something in the corner, 76.374.784. Still, that's not converged with respect to basis set because we haven't done the extrapolations. But when we do that, this table is from a paper that I'm currently working on for the H2O molecule, the water molecule. Most important molecule in biology, most important molecule in atmospheric science. The H2O molecule, I'm going to be publishing a paper on that soon. And this is what the table looks like. So for your molecule, you're going to have to do bigger calculations with bigger basis sets, but that means you're going to have to learn how to do more. You're going to have to get better with computers, specifically how to run calculations in parallel on multiple cores at the same time. And so that's ultimately what I hope you're excited to do next. So thank you very much for your attention. That's my last slide. And I hope that I didn't go too fast, but you'll always be able to watch this on YouTube later if you think you missed something.